Good afternoon. Let's get started. Next week, hey Vijay, how are you? Next week, we don't have a speaker, but we have a very special event. We have it every semester. It's the Energy Open House, where we just come in. We have food, we have soda, and we just talk about energy research, energy teaching ideas, and how we can take this platform even further, how can we make it more productive. So please join us. It's a very good event where you can network with other faculty, staff, and students from other departments and schools. Before introducing our speaker today, it's a really special pleasure. It's going to be a great talk. I would like to announce that this event is co-sponsored by AEP, which is the Alliance for Energy Policy. And what we do, so the co-sponsorship is really trying to work together with other student bodies on campus and increase participation and awareness of this event. If you have your own student group and you want to interact with us and do events together, we welcome that input, and please either reach out to me or my TA, Trevor Goodwin, and we can work together. And with that, let me share this with Michelle and tell you a little bit more about AEP.
Hi, I'm Michelle. I'm with the LBJ Alliance for Energy Policy. We are a student organization up at the LBJ school concerned with all things energy and environmental policy. We do a lot of networking breakfast and some field trips to different sites around town and some happy hours, of course. So we'd like to get to know you. If you're interested in our group, we're having a happy hour after the talk today. You can walk over with us at Crown and Anchor Pub really close by. So, thanks.
Thanks, Michelle. It's a great pleasure and really great one to introduce my colleague, Professor Brian Korgel, who is a professor of chemical engineering here, and he's also the director for the Industry University Cooperative Research Center on Next Generation Photovoltaics. And I learned this a few weeks ago from Brian. It's a really matter of pride for us. It's the only NSF PV center in the country. Is that right, Brian? So it's a very special pleasure to have Brian tell us a little bit more about what's going on at the center. Brian received his PhD from UCLA. He has been a visiting professor at several places, including in Spain, in France, and also with the Chinese Academy of Sciences in Beijing. He has co-founded two companies, InnovaLight and Neon Technologies. His research is on nanomaterials chemistry, and he has authored more than 200 papers. He has been honored with several numerous awards, and the one that I would like to point out is that he was elected as a fellow of the American Association for Advancement of Science, the AAAS, in 2012. It's a great pleasure to have you here, Brian.
So thanks a lot for the introduction. It's a pleasure to be here. Does this thing move, or how do you... I want to move it out of the way so you can all see, but okay. So I have 40 minutes, so I'm going to talk about next generation photovoltaics in 40 minutes to a really broad and diverse audience. So what I decided to do is tell you a little bit about the technology, how a solar cell works, some of what we do in my group, and some of the approaches we're taking towards next generation photovoltaics, and give you a little insight into how we got into doing what we do and where we're going. Also a little bit about where photovoltaics industry is now, and also maybe where it could be going. So I pulled up a definition of photovoltaic from the dictionary, and so a photovoltaic device essentially absorbs light, converts it directly to electricity, and the key aspect of this, which is pointed out in the dictionary, is that it utilizes when you expose a material to light, it generates a voltage or utilizes that photovoltage, and it requires a junction of two substances. So when we tend to think about solar cells, or I think when people talk about them, it's sort of like silicon solar cell, cadmium telluride solar cell, copper-neum gallium selenide, not necessarily realizing that there's also this key component, which is the junction. either homojunction, where you have two types of doping levels in silicon, or a heterojunction, and that's really key to what the device is. So the basis of a photovoltaic is a semiconductor, and the semiconductor absorbs light. So a lot of different types, silicon, other semiconductors you've probably heard of, gallium nitride, germanium, etc. So the light comes in, the semiconductor absorbs the light. If you look at silicon, so when we talk about devices, we tend to talk about electrons and holes. Okay, I think most people know what electrons are, but maybe not everyone knows what a hole is. So the light comes in, and the photon energy gets transferred into essentially breaking a bond. Okay, so in the case of silicon, you create a conduction electron that's free to move, and it leaves behind a hole. Okay, and so the electron's negatively charged, the hole's positively charged, and so in the device, the electron is going to move one way, and the hole will move the other, and that's what creates the current, the photocurrent. So the photon comes in, it's absorbed, creates this excited species, an electron goes one way and a hole goes the other, and that's the current. So you have to have the absorber, but then you need this junction. Okay, so there has to be some driving force to separate the electron and hole, and if there's not, you form the electron hole and they just recombine, and you lose that energy. Okay, so you have one semiconductor that's primarily the light absorber. Then you have a second semiconductor that creates a built-in potential, electric potential. Okay, so in the case of silicon, you can have silicon that's doped with an impurity that gives rise to an excess of electrons on one side and an excess of holes on the other. So you don't necessarily need two types of semiconductors to form this junction, but the kinds of devices that we look at in my group are not silicon, and they tend to be heterojunctions. So you have one semiconductor that's the primary light absorber, and then a second semiconductor to create this junction. And so we talk about p-type semiconductors and n-type. So p-type that are rich in holes, n-type rich in electrons. So the electron goes one way, the hole goes another. So in the device now, you need to be able to, once those electrons and holes separate, extract out the electricity. And so most photovoltaics, almost all of them, are sandwiches where you have the light absorbing layer, you have the second semiconducting layer, and then those are sandwiched between electrodes. So you have one metal layer on the top and one metal layer on the bottom. And as you know, most metals you can't see through. So if you had, a piece of silver or something on the top and the bottom, no light could get into the device. So these devices tend to have some sort of metal on the bottom, like aluminum or something like that, that you can't get light through. But then on the other side, you have a conducting material that's transparent, and those tend to be transparent conducting oxides, or TCOs. So when people are talking about photovoltaic devices, especially thin film photovoltaics, they'll mention the TCO layer, and that's one of these electrodes that has to be electrically conductive, but it also has to be transparent. And for some devices, that TCO layer can actually be what's limiting the device efficiency. If you want to eke out a couple of extra percent, you have to change the TCO. Okay, so these electrode layers are also really important. If you have kind of the wrong metal on one of these sides, you can create electric potentials that actually prevent electron and hole injection into those layers. So those are really important. And then some sort of mechanical support usually. So if I'm thinking about cadmium telluride device, so a cadmium telluride device would actually be flipped slightly, but a cadmium telluride device would have this layer is cadmium telluride, this other layer is cadmium sulfide, then you have glass with a TCO on it, it's actually switched, but and then a kind of a nickel carbon paste is the other layer. Okay, so that's the basic design of every solar cell. Okay, so they're fairly simple devices. If I compare photovoltaics industry to the integrated circuit industry, they're really, really simple. Integrated circuits have 25, 30, 40 steps with patterning, very intricate patterning, and they're very complicated. In the case of solar cells, all of these interfaces are really important, but tend to be a little bit simpler. Okay, so photovoltaics utilize sunlight, which is obviously free freely available. I mean, there are issues with it, like it's intermittent, and if you live in Antarctica during the winter, it's dark all for a long time and stuff like that. Those are some issues, but when the sun shines, that energy is free. Photovoltaic electricity is not free, and that is because it takes money to make the devices. So it takes money for the materials to manufacture the devices, and then once you have the device, it takes money to operate them. Okay, so when I first started working in this field in like 2005 or so, everyone was really focused mostly on the materials and the manufacturing, trying to get that down. Now that's actually down pretty far, and it's these other costs that have become a big problem. So you have Department of Energy that has almost stopped funding fundamental materials research for photovoltaics and completely gone the other way, where they're funding research into reducing soft cost and labor and how to do loans better and things like that. Policy, which maybe to some of this in this group is great. But you know, I would say there are still issues with materials and manufacturing. It's just that some of these other issues are problems. And so there's a trade-off. If you think about the costs, you have materials and manufacturing as one part of it, and then these maintenance and operation costs and installation costs are the other part. And so we think about the economics in a couple of ways. First of all is how much do the materials of the device cost, how much does it cost to manufacture it, and then we think about the efficiency of the device. So we obviously want the devices to be as efficient as possible and convert as much of the sunlight or solar energy into electricity as possible. But there tends to be a trade-off that the more efficient the device, the more expensive it is to make. And the cheaper it is to make, the less efficient. And you obviously want to be something really inexpensive. But if you imagine that you had a solar cell that you could make for free, but then had an efficiency of 0%, obviously that wouldn't get you anywhere. So there's a trade-off. And so right now, these balance of systems costs or maintenance and operation costs are very dependent on the efficiency of the device. So you want to have the highest efficiency you can, but without having to spend exorbitant amounts of money as well. One thing to know about the efficiency of a device is that if we're talking about a single junction solar cell, so the kind of solar cell I just showed where you have one semiconductor layer, the theoretical limit to the efficiency of that device is about 31, 32%. Okay, so out of all the sunlight coming down, you can only convert 30%. So you can't create a perpetual motion machine where you're getting 100% efficiency from a single junction device. You can start stacking semiconductor layers and get away from that efficiency, and those are called tandem cells or multi-junction cells, and I'll talk about those later. And you can do that, but for a single junction cell, a little over 30% the limit in efficiency. So this is the PV technology roadmap that NREL puts out and keeps. So this is accessible online. This one's up to date, so it goes up to 2015. So it looks complicated. What they're mapping is, as a function of year, the record device efficiency for these various technologies. And they're grouped into a couple of classes. One is multi-junction cells. So these are cells that have more than one semiconductor layer and can get above this Shockley-Queisser limit of 31, 32%. Those are all purple. These tend to be made from materials, 3,5 materials, so like gallium arsenide, indium phosphide, that sort of thing. And there's a special category called single junction gallium arsenide, which are really thin films. And I don't want to dwell, I could spend 40 minutes talking about this chart probably, but thin film crystal gallium arsenide, for example, was a really exciting material, got a lot of people at DOE excited because there was a company called Alta Devices that created a single junction thin film gallium arsenide device that almost got to 30%, which is the Shockley-Queisser limit. So that was a big deal, and people thought, wow, you know, really thin layers. That turns out to be really expensive. That device is about $100 a watt. So way above $1 a watt. They're very expensive, but for example, the military is really interested in those because for them, lightweight and like the maximum amount of power per area, if you're wearing these solar cells, are really important. So for certain applications, you can have high cost, and the efficiency is really important. This dark blue stuff are silicon cells, crystalline silicon cells. So we tend to divide the technologies sort of conceptually into silicon and thin film materials. And so thin film material, so silicon is an indirect bandgap semiconductor. Its bandgap is indirect, and because of that, when you absorb a photon, you also have to create a lattice vibration, a phonon, and that light absorption is very weak. So in order to absorb all the light by silicon, you have to have relatively thick layers of silicon. So this is one of the challenges with silicon, is that you have to have fairly thick layers of silicon, 50 microns thick, to absorb all of the light. And that means your solar panels can be relatively heavy, and you're going to have to use a lot of silicon. People have been working on thin film silicon, but inherently you're fighting nature with those. Materials like gallium arsenide, materials like cadmium telluride, copper-indium gallium selenide, those materials are direct bandgap semiconductors and much, much stronger absorbers of light. So you only need a couple microns thick of material to absorb all the light. So that class of materials are called thin film solar cells. And amorphous silicon turns out to have a direct gap, and it's also thrown into the class of thin film materials. So you have these 3,5s, these multi-junction cells, single 3,5 material. Then you have essentially polycrystalline single crystal silicon. Then you have them grouped in this green class, or these thin film technologies. And then in the red class, just everything else lumped together. Dye-sensitized solar cells, a new class of materials called perovskite solar cells, which are really exciting. Organic photovoltaic materials, quantum dot solar cells as well. So out of all of these materials, the tandem cells are for sale. Okay, so NASA basically buys those, so they can be 40% efficiency, but they're very, very small area. They're made by molecular beam epitaxy, and they're extremely expensive. People have tried to put those out on solar farms using big giant magnifying glasses to so solar concentration to make the economics work, but hasn't really worked yet. So those cells, people tend to say, are really for space applications and not terrestrial applications, even though they're trying to use them for terrestrial. The silicon solar cells, that's mostly what you find residential on houses, are mostly silicon. And then out of the thin film materials, amorphous silicon has been around a long time, but has limits in stability, photostability, and efficiency. So it's sort of stopped being used very much anymore. Cadmium telluride is the big one. So First Solar makes cadmium telluride. About 10% of the market's cadmium telluride. The rest is silicon. And then copper-indium gallium selenide is another thin film material that there have been a lot of companies trying to develop commercially. They do sell solar panels. There was a company in town called Heliovolt, which has been trying to commercialize that stuff, or had been trying to commercialize that stuff for a long time. And so out of all of these materials, there are only really a couple that are making a lot of money. So polycrystalline silicon, single crystal silicon, and cadmium telluride. Okay. So where I begin my own story is around 2005. So I graduated from UCLA in January 1997. Before that, I was trying to find a postdoc, and one of the first postdoc proposals I wrote was actually on trying to make solar cells from quantum dots, from cadmium selenide. I ended up going to Dublin, Ireland, and worked at University College Dublin, and made quantum dots or made nanocrystals, but didn't do solar cell work. After that, I really hadn't thought about it that much until about 2005. And at that time, the reason I started thinking about this was really because of one of the companies that I'd started. So I started a company called Innovolite with a couple of guys at Arch, which is a venture firm, Clint Bybee and Paul Turk. So back in 2001, We created a company where, in my group, we're making silicon quantum dots. The idea was to make light bulbs out of stuff. So light-emitting diodes. We wanted to replace the incandescent bulb with silicon quantum dot LEDs. And that turns out to be a really tough challenge. And so after a few years, we realized, okay, we're not going to get there. And thought, what can we do with our silicon, colloidal silicon quantum dots? And so started to work on solar cells. So Innovolite actually developed something they call a silicon ink, created a really nice facility in the Bay Area, had 85 people, and in 2011 DuPont bought it. So now this Innovolite is called the DuPont Research Facility in the Bay Area. But this was around 2005 or so. And so one of the initial ideas for our silicon ink was to actually paint a solar cell with silicon. The problem with that is you're taking an indirect bandgap semiconductor material and painting it on, and you have to use a lot of material to absorb the light. So it didn't really make sense to try to do that. What the company ended up doing was taking the silicon ink, and it's highly doped, and you make selected emitter devices on single crystal silicon. That's what they were doing. But I was thinking, is there a different colloidal material that we could make that you could paint on a surface and make solar cells out of it? And I happened to be on sabbatical 2007 or so, and so sabbaticals are great. You start thinking about things and get out of your environment. And so this is in Cadiz at the south of Spain. Someone was spray painting nano all over the place, and it wasn't me. It was somebody. I did not do that. But I was thinking, okay, well, what could you use as a paint for photovoltaics? So you don't want to use a material that has an indirect band gap. You want to use a material that's a strong light absorber. You want to use a material with a band gap of about 1.1 to 1.3 EV. And what material would that be? And if we look at this roadmap, okay, there aren't a whole lot of semiconductors that actually work. There's silicon, there's cadmium telluride, there's copper, indium, gallium selenide, there's some 3,5s, and then some more exotic materials. And there was some work being done at Berkeley on cadmium telluride at that time. And going back to 2005, people really didn't know how to stabilize cadmium telluride devices. It took some work done out of NREL and out of Colorado State to figure out that if you sprinkle a little bit of copper at the contact for cadmium telluride, you stabilize it, and thus First Solar has been able to make lots and lots of money. Without that innovation, cadmium telluride was dead in the water. SIGs, on the other hand, was relatively stable. It was a stable material, had a higher record efficiency than cadmium telluride. It's a direct bandgap semiconductor. And I'm a nanomaterials chemist, and so I was also interested in it because nobody had made nanocrystals of copper and gallium selenide. The way we do our chemistry is we have a beaker of solvent, and we throw in some reactants to make a material. So if you want to make a quaternary compound of copper, indium, gallium selenide, you have to put 4 elements into this flask, and those things can react in multiple ways. You can get multiple different phases, and so it's not obvious you can actually make this material. And so that's kind of where we started. It was a really interesting synthetic challenge, really interesting material that nobody had made in terms of nanocrystal solar cells up to that point. And so that's what we started to do. And the idea was to make an ink that you could spray paint onto a surface and make solar cells. And so after a couple of years, we figured out how to do it. It actually turns out that these class of materials, these chalcopyrite compounds of copper, indium selenide, copper, indium, gallium selenide, turn out to be really stable. And so you literally can just combine 4 elements in a flask, heat it up, and you get the chalcopyrite compound. Under certain situations, it gets a little more complicated than that, but it's really actually pretty straightforward. And so this is one undergrad that was working in my group, Daria Reed, and so she happened to be in the lab working when the television crew came in, so she got to be on TV making some nanocrystals, and a couple of undergrads doing some work at that time. So the SIGS device is glass with a metal back contact. This ink is what we're trying to deposit, and then a top layer. If you want to paint an entire device, you need to have inks or paints for all of these layers. And so We haven't gotten to that point. We just paint on our absorber layer and then vapor deposit zinc oxide and ITO on the top. But back in 2009 or so, we were getting just spray painting, just about 3% efficiency at that time. And we could do that on plastic. So it's not really commercially viable, 3%, but at the time that was the record for like a nanocrystal device, okay? So back in 2010, now on the roadmap, they added sort of printed quantum dot cells. And so there was a study on lead sulfide quantum dots from NREL, from Art Nozik's group, where they were at about 3%. So that's their point. That's about where we were at that time with this material. Okay, so Reader's Digest, for example, learned about what we were doing. Somehow, I don't even know how. Like, and this writer from Reader's Digest called me and was talking to me about what we were doing. And I was telling him, yeah, we spray paint this absorber material and make these solar cells. And he was like, wow, that's really cool. That's so neat. And I tried to explain to him, but our efficiencies aren't really that good. I mean, it's 3%. That's really good for our field, but it's not commercially viable. And we've got to get the efficiency better. And he said, it doesn't matter. That's like amazing. And so we made this is not number 2, it's number 12 of the, it's cut off on the side. But number 12 in the top 25 inventions that will improve your life. I think that was like 2011 when they wrote this. But, you know, the goal is really, okay, you can make these solar cells, but now to make them commercially viable, you need to make them more efficient. And there are a lot of challenges with that. So that's kind of how I got into solar cells. And if you think about how solar cells are deployed, you have utility scale, so big solar farms, you've got rooftops, so residential solar cells, and then things like solar backpacks. Okay, so this was a backpack made by Kanarka, which went out of business a few years ago. So maybe one day you can buy these again when the next Kanarka 2 or whatever arrives. So how do you get from new materials to the field? And that's pretty challenging for photovoltaics because the devices themselves are simple on the one hand, but complicated on another. Like each material has engineering, manufacturing challenges. The interfaces all have to be right. And then you have to scale these things up. It's a little different than integrated circuits where you're trying to make everything small. In some sense, that does create some challenges, but it's in some ways easier to make things small. In photovoltaics, you're trying to make everything big. And so it's really scale, how do you do high throughput processing, how do you use materials that are inexpensive. And so I started this center, this Industry University Cooperative Research Center. It's an NSF program. We have 2 sites, one at UT, one at Colorado State. And this program is basically, it's been around for about 35 years in NSF. There's about 70 centers right now. Ours is on photovoltaics. And the idea is bringing industry and university together and also creating a consortia of industry members. And if you think about, or if I think about the photovoltaics industry, it's really complicated, okay? Some companies like First Solar, for example, who started out as a panel manufacturer, realized the best way to make money is to be bigger than that. So they do much more than just manufacture panels now and are being really successful in that way. But most companies aren't large enough to do that, and they all rely on each other in this ecosystem, and they all have problems to develop. So if I'm going to talk about next generation photovoltaics, we sort of need to define current generation photovoltaics, and this is where we are. So in the United States, in the last 12 months, there's been about 4 gigawatts of utility scale power purchased. Okay, and this 4 gigawatts has been purchased not because of anything about government subsidies with the environment, but actually because the solar photovoltaic power is cheaper than any other source. Okay, so this is it's a new time for photovoltaics in many different ways. This is a picture of the Topaz facility, which was made by First Solar. So those are all cadmium telluride solar cells. It's about 550 megawatts, built in 3 years. It's pretty amazing. 9 million solar panels covers 9.5 square miles. So these are like mega solar farms, and there are a few of these in California. California has been really quite aggressive about trying to create these. And if you compare like how much power that is, this, for example, this is the Glen Canyon Dam, which produced about 1.3 gigawatts of power and took 10 years to build. Okay, so that's sort of the scale. And this is where these things are being deployed. So that 4 gigawatts is not just in one particular state. It's actually distributed around the country. And so there are even a couple in Texas. Okay, one trend that's sort of happening, there are these mega solar cells of 500 megawatts, and those can be made under really certain special conditions in terms of the land. But probably more generally, what we're going to see is 10 to 100 megawatt facilities, because you can insert those more easily into different places in the land. So if you look for the cost of solar, this is from a report, Lazard's report. Again, it depends a lot on the actual conditions, but if you look at utility scale, solar PV, and compare that to like natural gas, they're on par, okay, in certain places. So it's really a unique time for photovoltaics, and I'm not sure the general public really realizes this. Most of the general public thinks about residential solar, and residential solar is still fairly expensive. Okay, so the Sunshot goal has been $1 per watt, so it's a little difficult to go between price per peak watt, which is during the day with the most sun, to price per kilowatt hour of electricity, but you can do some things to get there. Getting to about $1 per watt is about grid parity with natural gas, and the best residential is getting down to about $3 per watt. So that's dropped almost about $1 or $1.50 in the last 2 years or so. So it's come down quite a bit. And if you look at the costs, the relative costs of all of the components, this is the module down here, which is about 70 cents or so. And so most of the costs, this is the reason DOE is focusing so heavily on these soft costs, is because that's really important. That's where most of the costs are at the moment, including labor. So people are discussing how do you drive down the labor costs. And if you think about comparing us to Europe, for example, there was a study done out of Georgia Tech. This was end of 2013, so it's a little old, but I think it's still pretty relevant, showing that if you compare the cost of residential solar in Germany to residential solar in the US, it's not the module that's the difference in cost. It's the labor, the permitting, the installation that makes the cost of solar in the US much more expensive. And so I learned this sort of firsthand. So I had a graduate student, Taylor Harvey. We did something called the I-Core program. So this is a program through NSF. It's called Innovation Core. We now have a node doing this at UT. Heath Knockin was our business mentor. And so the idea of the I-Core is you put in for a grant from NSF. NSF gives you a little bit of money. Then you go to this node, and they teach you how to do customer discovery and figure out if you have a market for your invention. So we had this semiconductor ink where we can print solar cells, and the idea was, is there a market for this stuff? Are we at the right point where we should start a company to try to develop this or not? So the first thing you do is figure out, what's your competition, and the goal of this is to do a bunch of customer interviews. So in the course of 6 weeks, we did 114 customer interviews, and one of the things we learned almost immediately was that the issue in solar is not really how much these panels are. And again, it's obvious if you look at this economic data, the panel cost is relatively low. It's labor and installation. We interviewed someone from New York City, and they told us that permitting for solar cells is $4 a watt in New York City. So if you're trying to get $1 per watt and it's just $4 a watt, 10 minutes, okay. I was like, I don't think it's 10. So $4 per watt for permitting in New York City, and they were like, and Texas is one of the lowest, like $2 per watt. But that's just for permitting and installation. So you start to realize, if you're thinking about your technology, which is entirely new and untested versus others, you're really not going to necessarily beat them unless you do something entirely differently. So what we learned is, these sort of flexible types of solar cells are where we need to compete, because SIGs is like $7 a watt and morphosilicon's 10. Silicon still dominates the market, so almost 90% of the market is still silicon, even though CAD telluride is getting cheaper and better. In some ways, so is silicon. So most of it's silicon, but in terms of trends in the market, and this is because First Solar is a pretty amazing company, they continue to reduce the cost of cadmium telluride, and people believe that by next year it'll be equivalent to polycrystalline silicon. Okay, so what's next generation PV? Next generation, reduce these soft costs. So again, DOE actually funded a roadmap on soft cost reduction, and so it's like, how do you reduce labor costs? Okay, and when you get to the red, it's like, well, they don't really know quite how they're going to get there. I don't know. So these things, that's one trend. Business realizes that photovoltaics are really important to their business. I think Apple's putting a huge facility in Arizona, basically just so they have redundancy for their whole computing thing. So if the power goes out, they still have power. Walmart, I guess that little yellow sun on the Walmart sign maybe means something. They use a lot of solar power, and so those costs are being translated to cheaper products. This is one of my favorite ones. Get Texas involved. So if you look at the top 10 states doing photovoltaics installation 2013, Texas is not there. We obviously have a lot of sun and a lot of land. Okay, so we should have some solar. So at least in 2014, there were a couple of these utility installations going in. So now it's on the list. The challenge in our state is the oil and the oil lobbying, I would say maybe. Okay, so but Texas would be a great state for solar. If you look at the worldwide trends, solar installations are going up. They're continuing to go up. And I don't think that's going to stop. Again, Europe is really leading the way. And, Germany has the highest PV capacity in the world. And when you talk to people about solar, they say, oh, you can't have solar in a non-super sunny country. Germany's not super sunny. They've got the biggest capacity in the world. China just moved up to second, so they surpassed us. And then Japan is right behind us. The unfortunate thing is, even with these trends, the predictions are that worldwide energy use is going to energy needs are going to continue to increase, and most of that's going to be met with things like coal and natural gas. And renewables will continue to expand, but only be about 5% of meeting the energy needs. So from my perspective, what do we have to do? On the one hand, photovoltaics looks great. Capacity is going up. You're utilizing a lot more solar energy than you ever had in the past, but we're still really quite limited in terms of what we'll use. So this is when I think of next generation photovoltaics, this is really the issue. How do you change that dynamic? You've got to keep the costs of the solar modules down. You've got to lower the soft costs, which essentially means make really inexpensive but highly efficient devices. And this is really what the whole field's been doing for the entire time it's been around. But how do you get there? This is our sort of part of our roadmap in our center, is going from a single junction cell, like maybe it's based on cadmium telluride, maybe it's based on SIGs, maybe it's based partly on silicon, but getting to multi-junctions or tandem cells. So by doing that, you can potentially dramatically increase the efficiency of the device. There are a lot of challenges. Every semiconductor layer has to work really well. You have to have the junctions or the interconnects between layers have to work really well. You have to have current matching, and nobody really knows how to do that at the moment. So that really is a next generation, future challenge. But if you could get to thin film devices that cost the same amount to manufacture as they do now, but with 35% efficiency instead of 16, that'd be really important. The other thing that I think about a lot, because it's maybe more relevant to the work I do in my group, is thinking about new ways of deploying and using photovoltaics. So I was looking, there's an artist working in my group named James Sham who's doing all of these things with photovoltaics and creating sculptures and things like that. So I was curious to see what are other artists doing, and there's this person named Sarah Hall who did this really interesting stuff. This is actually on a church, and she's known for stained glass, and it's stained glass, these stained glass windows with photovoltaics embedded, and it looks amazing. It looks really beautiful. So this idea of integrating photovoltaics, maybe into buildings that you wouldn't otherwise do it, and you're generating power in that way, okay? And I think there are a lot of potential things we can do in this direction, even with existing technologies. The other thing is lightweight portable PV is still a major issue, partly because of just the form factor of most photovoltaics, making them truly lightweight, really flexible, and then integrating them with energy storage devices with batteries, because that's a major issue at the moment as well. So those are future issues. So I would say those are some of the trends I see anyway that we're thinking about, is really low cost, ultra-high efficiency devices, still a major challenge in the field, and then photovoltaics with different form factors than you've ever been able to use before. So I have 3 generations of photovoltaic students, first gen, second gen, third gen. So I still show all these guys have graduated, Vahid, Brian, and Matt, but they started in the lab from really nothing. Like we had no infrastructure, we had no solar cell testing set up at UT, even the vapor deposition equipment we had to buy from scratch and install. There was really very little, if almost none, photovoltaic expertise at UT when these guys started and took the project to sort of that 3% printed device. Then I had Chet and Jackson and Taylor kind of take over and do some pretty interesting things. Taylor's the guy who went through the I-Corps program, and he, as a result of that, started a company. So he just graduated in December, and he actually created his own job. He started a company with one of my former students, Aaron Chakla, this company called Lucello, and they were able to get an NSF SBIR grant. So he wrote that while I was a PhD student. They got the grant, and he has company, so he just went from graduating to working for himself. So that was pretty good. All you students out there, think creatively. We have an I-Corps node here now. You can go, learn how to start a company, become rich. And then these guys, Doug Pernick, Vikas Reddy, and Sherelle Thomas, who are kind of now in it, trying to take the technology to sort of the next stage. So anyway, that's all I have to say, and be happy to answer questions. Thanks. Yeah.
Let's do student questions first. Any students? Is it working? Yeah.
Howdy, sir. My name is Kevin Merrill. I'm a master's at LBJ student. Thank you for the talk. It's very interesting. One of my biggest qualms with going to a solar panel power structure for my house is that the life expectancy of the grid itself has to be replaced, from what I understand, about 10 to 15 years down the road. And then what is the likelihood of the grid ever actually recouping the cost of installment from the savings that I would get from going to solar?
The grid, you mean?
My solar grid,
Okay,
getting me
what
off
you're
of city
installing.
power, that's the biggest qualms that I have with solar.
Yeah. Well, I think a lot of the companies are warranting their solar panels for 30 years, or at least 15, maybe more like 20 to 30. But some of the cost models or the business models people are going to now are doing kind of like leases on solar cells. So I'm not sure if they do this too much in Texas, but I know like in California it's very popular where people will basically sign a lease and it'll be attached to the house for like 30 years, which has other issues. Like when you try to sell the house, you're stuck with that solar panel. It sort of gets passed on to the next person. But that's one way that. So again, I'm not a business expert, but the industry is thinking about these issues that you're thinking about and thinking more creatively about how can everyone sort of benefit. You benefit as a consumer from cheaper electricity, but then these companies are taking a cut off of what you save, right? Also, if you have residential PV and you are feeding energy back in the grid, like they buy it for a really low amount, and so there are all of these things. And I think right now the best, people are trying to find the best business model. That's actually part of these DOE studies, is thinking about loan structures and things like that. But I think most of the panels I know of, I think, are warranted for 30 years. They might not last that long, but then the company has to replace it. So.
Hi. I was wondering if you could talk a little more about what the end vision for the solar spray looks like. And whether you envision that being like something you go buy at a hardware store and spray it on your car, your windows. Where do you hope to see that go?
Yeah, I mean, so what Taylor's trying to do are kind of like photovoltaic labels, so like disposable photovoltaics, and there's potentially a small market for things like that. So you would. A lot of these solar cells, to get high efficiency, you've got to use relatively high temperatures to crystallize the material. So if you want to make solar cells on paper or like polyethylene, the stuff your garbage bags are made of, then you need to be able to deposit materials at very low temperature. So that's essentially what we're trying to do, is use incredibly cheap materials and lightweight as substrates. The issue is that even if you have that, for something like residential, like rooftop power and things like that, you need to get to reasonable efficiencies, like maybe 10% for some applications. And so that's where I see it going, essentially trying to make solar cells with 10% efficiency that are dirt cheap, that you can just mass produce, that have with a form factor that haven't been made before. Again, you end up competing with existing technologies, and so whether there's a market there for that or not, I'm not really sure. But I see that. My other thing that I see myself as is maybe stirring the pot a little bit, because I came into this not as like someone who studied photovoltaics for their entire life. I'm come into it new, and I'm like, well, why do you make a solar cell like that? Do you have to do that? And then everyone tells you, yeah, we have to do it the way we're doing it. And I like to, I think as academics, we should be asking those questions and forcing people to really maybe re-examine the way they do things. And so as an academic, that's one of the things that I see, and inspiring a lot of people to think about solar cells and maybe do research on it, even if they use a more conventional way of doing it, inspiring people to think a little more differently.
A question over here. I'd like to ask you, well, first of all, I'd like to thank you for your presentation. I'd like to ask you about a technology that I didn't hear you mention, well, two actually. The first one is graphene and what you think impact it might have on overall efficiencies, simplicity of manufacture, cost-lowering effects. And the second one is by a company that, if I remember this right, is called Natcor. They have patented a process by which, currently chemical vapor deposition is used in the conventional silicone cell market as a technique to reduce reflection, to increase absorptivity of the solar cell. And CVD is problematic. It's a bottleneck for manufacturing. The machines are terrifically expensive. It produces silane as a byproduct, which is toxic and has all sorts of chemical storage and handling requirements. Their technique involves a liquid bath doping of the panel followed by femtosecond blasts of high energy lasers, which knock pits into the silicone. And these are supposed to be photon traps. And the idea is that, you get a much higher absorption and therefore much higher efficiencies in a process that is cheaper. And do you know anything about this, and what is your long view of that?
Yeah, well, I can answer. So the graphene issue, we actually have or had a project within our center looking at graphene as a replacement for the TCO layer. So graphene is one carbon atom layer thick, so it's quite transparent, but then it also has metallic conductivity. So you could have a very highly transparent, electrically conductive material. The issue with graphene is that because it's only one atom thick, you actually get relatively little current flowing through it, even though it's conductive, conductivity is high. So I don't really see graphene figuring into it too much, but people. This issue of a replacement for indium tin oxide or something like that is a huge one, and people are working on that. I just don't know that graphene is going to be. I don't think that'll be the one that wins. In terms of this pitting, I don't know anything about the company you're specifically talking about. The issue of light management in every solar cell is really important. So you usually kind of roughen the surface to prevent reflections. Solar cells are all, the silicon solar cells especially, there are companies that's what they do. They come up with strategies for light management. So it's not surprising to me that there's a company working on a way to do that might be more cost effective. But that's a tough business. I mean, people have spent a lot of time trying to figure that out. You need something really inexpensive, and that's compatible with your process strategy. So, but I don't know about that company.
Yeah. Thank you again. Great presentation. Can certainly understand the leveraging effect of having the tandem and the triple junction, given its multiplier effect on the balance of system cost. And since there's already existence proof that they work, just in NASA and such not, can you describe a little bit more in detail some of the key challenges in cost reducing those to get those to a price tier that would be competitive with the technologies that are pervasive today? And are there going to be convergence or divergence with, say, what Intel spends for $5 billion fab in process modules with applied materials? Are there more speciality that's needed to create the process modules for that type of technology, or can you get some trickle down where once Intel's created 14 nanometer microprocessors and that's old technology, that you've got depreciated equipment that can radically reduce the price? So is it converging or diverging with the high-end, say, processing silicon modules, and what are some of the other cost drivers?
Right. Yeah, so some of the main issues with the tandem cells are, for example, you have to match the currents through the cells. So you have to, first of all, every one of those layers has to work sort of as well as the other one, otherwise the one limits, and that is a challenge for sure. Stacking these layers, once you make a bottom layer and you put a top layer on it, if you have to heat that entire thing to 550 C or something like that, you can damage the entire device. So, making all the processes of each layer consistent. Then the other issue, the thing that got the 3-5 tandem cells to sort of work was figuring out how to do the tunnel junctions. And so nobody really quite knows how to do that for like what these interlayer materials should be. There are probably some lessons from the 3-5s that could be utilized. But there's some those are the challenges. It's really the junctions and making sure each device layer works well. And those are a lot of engineering challenges. I think people can pick semiconductors with the right band gap for the most part, but then how do you make that and do it reliably? In terms of processing, I think the challenges, when you do the tandem device, you're obviously adding steps to these things. In some sense, kind of the holy grail to this would be having process steps for each of these layers that you could translate into a roll-to-roll process. So you're basically just taking your substrate and just rolling it through the factory. And so then you'd be adding, different deposition tools, but you wouldn't necessarily be adding a lot of time to the processing. Because if you have to add a lot of time for each one of those steps, then that makes the economics go. Yeah, and the CAD Tellurides actually roll to roll. I mean, these are glass panels, but it's amazing. I mean, it's incredible what they do. They just sublime, and these are vacuum processes, but they're not ultra high vacuum like chemical vapor deposition. So they're quick vacuum changes where you do a quick sublimation of CAD Telluride and then into CAD sulfide, et cetera. And that's a roll-to-roll process. I think they're doing like a panel and like the whole thing in like 2 minutes. It's amazing. That's why CAD Telluride's so inexpensive. So silicon is about the same price as CAD Telluride, but it's because it's heavily subsidized by China, by the Chinese government. The actual it's amazing what they've done in China with the scaling and getting the cost down, but there's still a lot of subsidization of the cost. Whereas CAD Telluride, First Solar is an American company in Arizona, and there's nobody's subsidizing them. It's actually really, it's amazing.
Thank you for your presentation. One criticism of PV panels is like the intermittency, and so I was wondering if or how like storage technologies are working with PV, not just like electricity storage, but also like maybe thermal storage as well. I'm just wondering if you have any insights on that.
Yeah, no, I mean any type of storage. So people are looking at a few things. So within my center, I'm actually really trying to recruit some battery companies or people who do storage, because that could be a big market for their storage applications and solve a big problem in photovoltaics. So the intermittency is definitely an issue that needs to be dealt with. One way people are doing it is, well, the way everyone's doing it, I suppose, is you have solar and then you have something else. And so there are systems issues, just like what's the best way of optimizing how those two types of energy systems interact or work together to meet the needs. So there are like systems and optimization, control issues. But yeah, storage is a big problem, and yeah, massive energy storage. We need it for PV, but we need it for almost every renewable technology. And if we had a really good way to do it, we could have good electric vehicles and things like that.
I have a question to follow up on the comment you had there about, I guess, the manufacturing or the engineering sort of processes between CAD Telluride and crystalline silicon, in terms of, I guess, the level of vacuum you need, or the temperatures, or the time at certain temperatures you need. Mm-hmm. From a life cycle standpoint, I guess you feel confident you could sort of characterize that this technology is fundamentally cheaper from an engineering, manufacturing, knowledge standpoint because of the materials and energy inputs and time and
so you
vacuums.
mean cadmium telluride?
Yeah, CAD-Tel versus silicon.
So life cycle analysis isn't exactly in my area, but from what I've read, First Solar is really trying to, at least they're promoting the fact that they have, I forget what they call it, like cradle to cradle, They have their own recycle program and stuff like that. So in terms of resources like the cadmium and the tellurium and all of that, they have a long-term plan for how to keep recycling that. The processing temperatures are much lower, and cadmium telluride can, as a material, can sustain a lot more defects and impurities than silicon can. So silicon has to be really ultra pure in order to get decent efficiencies, whereas cadmium telluride doesn't have to be quite ultra pure. So that means your energy costs and purification steps are lower as well. There are people doing life cycle analyses. First Solar would tell you it's a lot better, but yeah. But I mean, the issue though is like there's definitely not as much cadmium and tellurium in the world as there is silicon, right? I mean, 28% of the Earth's crust is silicon, but you have to get it away from oxygen and everything else. So I think those are still some good, important studies. I know people are working on them. I don't know where people are at quite at the moment.
One final question?
Yeah, I wanted to nudge you over towards the policy area, and I noticed in one of your charts you showed Georgia. It looked like it had like 700 plus megawatts. So it looked really high compared to the other states, and I know they have a very good, currently a $5,000 EV incentive. And so, do you know anything about that, or what? I know you had some ideas. What do you think would be some good angles that state governments or the federal government could take to incentivize more residential, maybe more on a national policy level than state by state?
Yeah. So again, you're getting a little bit out of my area of expertise, but I think one thing is clear. Like California has just got way more PV than any other state, and they have more PV because of state policy, and have adopted a few different things. I think they have the highest. You have these, I forget the acronym, but these environmental thing, or the renewable incentives, where the state, I forget the acronym. Portfolio standard. Yeah, portfolio standards. I think California has some of the highest, and they continue to increase. And what I was reading is that California's wind resources are almost kind of tapped out, or they're sort of at the top. Like they only have so many windy hills in California, and I think they've got a bunch of windmills, and it's hard for them to keep expanding wind. Whereas with solar, a lot of California is desert, and like this Topaz solar farm is out in the desert. There's another one being built. And so those take state planning. And then you have residential incentives as well. So the other thing in California that happens is I think there's more, the utility companies don't necessarily like all the residential solar that's in California. It creates some issues with the utility companies and the grid management, and they complain about it. But I think the Californian government is such that they don't listen to them that much, whereas I don't know as much about Texas, but I think it's not quite that way in Texas, so I think the utilities have a lot more influence over policy for the state. And so I think that issue is important. I mean, so states can play a huge role. I think it's challenging for what the federal government can do, because a state like Vermont is not going to be similar to a state like Texas, right? So if the federal government steps in and says every state has to have this much solar and do it, I don't think a policy like that would work. So I think the states have to really step up, look at their geography, look at their resources, and then the state governments have to be kind of smart about it in some way. You know, I mean, I don't know. That's the way I see it.